Okay, so this task here is about recognizing important features of a velocity time graph. This particular graph was created by tracking the car around the streets of Paris in the film Rendezvous. So it shows the various velocities as he drives around famous landmarks in Paris. But what you need to do is to use the method in the previous task to calculate the lowest acceleration for the journey around Paris. Use a ruler, highlight the section of the graph you use, and label it lowest acceleration. Okay, so the lowest acceleration would be a portion of the graph that has got a positive gradient going up, but it's the lowest or smallest rise in gradient. So looking here, we've got a couple of sections here which are positive, but have got quite a low rise, and I think that those are probably the lowest two. So I would suggest that this here is the lowest acceleration shown in this graph. So it says to use the ruler, so I'll use the ruler here just to highlight that section of the graph. That's the bit we're after. Okay, and it says use a ruler again to draw vertical arrows from the start and end times to the x-axis of the sections you're going to calculate the acceleration. Okay, so what that means is this is the time axis across the bottom in seconds. We need to draw some vertical lines down in order to work out over what time period this particular part of the journey took. Okay, so if we move that down, now this scale is not brilliant. Okay, there's very few indications along the bottom here, but if we sort of estimate, there's 100 there, 200 there. Okay, so in the middle is going to be 150, so that's 160, and this is 200. So consequently, this time span here is 40 seconds. So that part of the journey took 40 seconds. And we could also draw that part there as a triangle. That's 40 seconds. And then it says use the ruler again to draw horizontal arrows from the start and end velocities to the y-axis of the sections you're using to calculate the acceleration. So here we need to draw an arrow that goes back to the velocity axis at the start velocity for this section and also at the end velocity for this section. Again, the scale on this graph isn't entirely useful, but we can probably estimate that's 25 meters per second increasing to 26 meters per second, making that a 1 meter per second increase in velocity. Okay, and then the final part of the calculation is to calculate the acceleration itself, and for this we need to remember that acceleration is the difference, the change in velocities divided by the time over which that takes. So we've just established that the change in velocity is 1 meter per second because the vehicle starts off at 25 meters per second and increases to 26 meters per second here, and the time of which the time that takes is 40 seconds. Okay, so the calculation is 1 meter per second divided by 40 meters per second, which is okay, so got 1 divided by 40, 0.025. Okay, so that's 0.025 meters per second. Meters per second squared. Okay, so this is in meters per second. This, of course, was never in meters per second. It was always just seconds. Okay, so that was a mistake there. Okay, so meters per second divided by seconds becomes meters per second squared. So 0.025. So a low number, which has to be expected because this is a very slight increase in speed, a very slight acceleration. It's a very shallow gradient. And then the second part of this task, it says use the method on the previous task to calculate the highest acceleration on the journey around Paris. So previously we were looking for the least steep line on the graph. This time we're going to be looking for the steepest line on the graph. And perhaps not surprisingly, I believe that could be this part of the graph here, because this is where he accelerates down a very straight road for a long time until he hits around about at the Arc de Triomphe. Okay, so we'll just double check there's nowhere else. This is a relatively steep line, but I don't think it's as steep as the first one. So I think this here is the highest acceleration. So we'll highlight that. I'm sort of ruling over the top of it, making it clearer. And this is the highest acceleration. And then once again, we need to calculate what the acceleration actually is. So again, we need to drop these arrows down. We don't need to drop one for the starting point, because of course it is on the x-axis. Okay, but here is 0 to 100. And then we've got our 50, and then we've got 1, 2, 3, 4, 5. So we're talking here about 9 seconds. And here we're talking in the region of 20 seconds. So we'll call that. So the difference in that, so 20 take away 9, of course, is 11 seconds. So this acceleration here happens over a period of 11 seconds. Okay, so a car is sets off from a standing start and accelerates rapidly over a period of 11 seconds. At this point, where he decelerates, will be where he has to brake, okay, to avoid crashing into the Arc de Triomphe. And then the change in velocity, okay, so it's actually very similar to the end point there, but slightly higher than the previous task. We'll call that 27, and he starts off at 0. So of course, 0 to 27 is a change in velocity of 27 meters per second. So again, we need to use these two values, 27 meters per second and 11 seconds, to calculate the acceleration. Acceleration is change in velocity divided by the time over which that occurs. So the change in velocity is 27 meters per second, and the time over which that occurs in this particular case is 11 seconds. Okay, so 27 divided by 11, 2.45. Okay, so 2.45 meters per second squared, which we can see is 2 orders of magnitude, 2 powers of 10 bigger than this acceleration here. Okay, so this is a very gentle acceleration. This is a much faster, much higher acceleration, therefore much faster. Okay.